Hi, today we will take a look on this instrument. So this is the first LCR meter I have designed when I used to work at Rameg Instrument in France. Now this is a 25 kHz LCR meter. So first, let's have a look on the block diagram of this instrument, and then we will take a look inside. This is the block diagram of the AT18. So I have designed these schematics in 2005, 15 years ago. And this is the classic design, which uses the auto-balancing bridge technique. So the impedance to be measured is in the middle, here, because an LCR bridge is first an impedance meter. The impedance is connected between a test generator, which is a high drive signal here, and the second terminal of the impedance is connected to a virtual ground, which is a low drive signal here, which is close to the ground in terms of potential. The high drive signal is a sine signal. The frequency of the test signal can be changed here. So we have the choice between different possibilities here. So you have the choice between 100 Hz, 120, 110 or 25 kHz. The current which flows into this impedance is fed to a transimpedance amplifier, which is built with this op-amp and the feedback resistor. So across this resistor we have a voltage which is proportional to the current which flows into the device here. Inside this box there is also a differential amplifier. The input of the differential amplifier can be connected to the reference resistor in order to measure the current. The input of the differential amplifier can be connected also across the impedance to be measured here. The measurement of current and voltage are done sequentially using this switch. So this switch permits to have the measurement of the current or the voltage. For the position of this block diagram, the differential amplifier is connected to this resistor. So this permits the measurement of the current. So the selection is done by this IV signal here. The transimpedance amplifier has 4 different ranges, which are selected by these 2 logic signals, R0 and R1. So there are also 2 other ranges, which are extended ranges, which uses actually one of these resistors here and one amplifier here. So this is used for the first range. In this case, the voltage across the device here is amplified. It is used also for the high range. In this case, the current is amplified. So this is the goal of this amplifier here. At this time, you have at this output of the amplifier an image of the current and an image of the voltage, depending on the state of the IV signal here. So now the goal is to measure an impedance. The impedance is a vectorial ratio between the voltage and the current. So in order to perform this vectorial measurement, we need to know the absolute value and the phase of both current and voltage in order to get the in-phase and the quadrature part of the voltage and the current. The signal at the output of the amplifier is fed to a phase detector. The phase detector is actually a multiplier. The second input of the multiplier is X signal, which is called the phase. In the AT18, the phase signal is a square signal. There are different types of phase detector. It is a simple phase detector which uses a square signal because it is very easy to provide the square signal. In the AT118, a multiplying DAC is used for the phase detector. In order to get the in-phase and the quadrature part of the current and the voltage, the phase signal here can be shifted by 90 degrees phase step. At the output of the phase detector, we will have a signal which is comprised by a DC signal and an AC signal which has twice the frequency of the test signal. What is important is the DC signal. The DC part of the signal is proportional to the amplitude multiplied by the cosine or the sine of the phase between the reference and the signal itself. For a given impedance at a given frequency, the in-phase and the quadrature parts will be measured for the current and the voltage. We will have at the end 4 measurements, 2 measurements for the voltage, 2 measurements for the current. From these 4 measurements, the firmware will extract the impedance, which is the vectorial ratio of the voltage by the current. The DC part of the signal which is present at the output of the phase detector is measured with a dual slope ADC, which is here. So in order to remove the AC signal, which as I said has a frequency which is twice the test frequency, So in order to remove this unwanted signal, the ADC is synchronized to the test signal. So the integrating time will be a multiple of the period of the test signal. This synchronization is performed using the CPID, which is inside this CPU here. The CPU which was used for this instrument, the CPU from ST, it is the family of UPSD. The UPSD family from ST is based on the 8032 core with additional features. The additional features is first CPLD. So there are several versions of microcontrollers for the UPSD family, maybe 15 or 20 different versions. So depending on the version, you have different amount of flash memory and a different number of cells also. So you can have a version with 16 cells and versions with 32 cells. This is interesting because you can include some glue logic inside the microcontroller. The last thing is the stimulus generator, which is on the left of this block schematic. The stimulus generator permits the generation of a sine signal at a given frequency. In this instrument, a square wave is used, which is present on this line here, which is called fsig. Here, the square signal is fed to a low-pass filter, which is an elliptic filter. You have the choice between two levels, and the bias can be added also. So then this voltage is fed to an output buffer, and there are different source resistors, which depends on the range of this instrument. And then the signal is fed to the device under test here on high drive signal. On this block we have also the phase signal here. The signal is fed to the phase detector as we have already seen. This is this signal here. These two signals here, PHA and PHB, permit to change the phase of this phase signal with 90 degrees step. The phase can be changed from 0, 90 degrees, 180 degrees, and 270 degrees actually. So this permits to remove the offset of the measurement chain. And also, as the final measurement is the ratio between the voltage and the current, all the errors which are caused by the reference voltage of the ADC and the different gains of the ADC and other stuff are compensated, because actually, except for the first and the last range, the same amplifier, the same phase detector and the same ADC is used. That means that the drift of the phase detector and the gain of the ADC and the voltage reference are automatically compensated. The final accuracy of this instrument is mainly defined by these reference resistors here. That's the end for this first part about this AT18 LCR meter. Next time we will see how to calibrate this instrument, and we will perform some measurements on the internal circuits. Thanks for watching and see you next time. Bye!